Okay. Welcome everyone to Data Structures and Algorithms. Uh, I am Boan.
I'm Lucius. Sorry for the mic problems just now.
Hello everybody, I'm Kian.
And this marks the start of the Data Structures and Algorithms workshop. So firstly, I'll pass it over to Lucius to explain algorithmic thinking.
So for this workshop, we'll be covering different topics, namely algorithmic thinking, recursion, data structures, and some other additional problems. And if you haven't already done so, please create a Codebreaker account and get your account approved here as soon as possible. I'll send the link in the chat. So you can open a Codebreaker account and get your account approved at that Google form link. So without further ado, I'll start on my section, which is on algorithmic thinking. So what is algorithmic thinking? Algorithmic thinking is a structured way for solving problems, especially in competitive programming, by breaking them down into a series of clear logical steps and algorithms. It enables us to understand complex problems and develop possible solutions for these problems. So what is an algorithm anyways? So an algorithm is a set of finite rules and instructions to be
Lucius,
followed.
sorry. Lucius, we can't really see you changing the slides right now. Okay, it's good now.
Can you all see?
Yeah, it's we can see now.
Can you see? Okay. Yeah. Sorry for the technical issues. I'll start again. Yeah. So I'll start on my section on algorithmic thinking. So what is algorithmic thinking? Algorithmic thinking is a structured method for solving problems by breaking them down into a series of clear, logical steps and algorithms. It enables us to understand complex problems and develop possible solutions for those problems. So what is an algorithm anyways? An algorithm is a set of finite rules or instructions to be followed in calculations or other problem-solving operations. So as you can see from the diagram over here, we have an input, and then we have rules or instructions to produce the output given the input. And then we have output at the end. And many times in programming, especially in competitive programming, you may encounter complex problem statements or complex problems that require
Lucius,
you
it
to.
might be like in. Do you change the slide from what is algorithmic thinking?
Yes. Sorry, what slide are you viewing now?
Oh yeah, sorry guys, some technical issues.
Yes.
We're on a bridge statement right now.
Yes. We are on a bridge statement right now.
Okay.
I just confirm that everyone is seeing the correct slide. I'm so sorry for the technical issues. So can you all see the slide? Okay. In that case, I'll continue. I'm so sorry for the technical difficulties. So many times you encounter complex problem statements. When problems are long, it makes it really hard to think clearly, and hence it makes it harder to arrive at a solution for the problem. So here is a sample problem that we have. So we can see that it's a bit long and it will take a while for us to understand it. And not only this, but there are even more complex problems out there. They are even more complex than this. Hence, we will need to break down the problem before we approach it. We shall now proceed to approach this problem. So firstly, what we should do is to refer to the inputs and outputs. So in this case, our input is the number n, the arrays a and b, and our output will be the maximum profit made. Then we'll identify the steps involved, in this case, buying AIs on day I and selling for a price of BI on day I as well. Hence, we arrive at the following abridged statement. Every day we'll buy A amount of stock and sell some of ours at price of B. And we need to find out what's the maximum profit, ignoring the cost to buy them. So you can see that this is the abridged statements that we have arrived at. And it's much simpler than the initial statements, which may take quite a while to comprehend. So in the problem statement, we may see also some sample test cases and explanations as well. So they show you how to solve the problem, but are often not the only solution. So you can see over here, this sample test case over here is for the exact same problem that I shown just now. We can see a sample input, a sample output, and the explanation. So over here, we can see that the explanation is not the only one that is also optimal. We can also see that we can sell 2 on day 1, 8 on day 2, and 22 on day 7, and still arrive at the optimal answer of 258. So we can see that the explanation is one solution, but it may not be the only solution in many times. So later during the algorithm section, you may find out that you may use a greedy approach for this problem. And spotting patterns like this is an important part of algorithmic thinking called pattern recognition. So I have a sample problem here. It is on Codebreakers as well, but you need not create an account for this specific problem. I'll give you all 5 minutes. You all can post what you think is the bridge statement in the Discord channel, and I shall start the timer now. Thank you. Yeah, 5 minutes has ended. I've seen a response inside the Discord chat. So it reads, Jia Hai has N potatoes, each with a unique mass, and he can process 1 potato per day, and has D days to prepare for a competition. And the goal is to maximize the total amount of mashed potato in kg he can make by selecting the best potatoes to process within the given days. So this is a perfectly good bridge statement that summarizes the problem succinctly. So good job. So here's the bridge statement that I have prepared. So given an array of n integers representing potato masses and an integer d, compute the maximum amount of mashed potato that can be made. So this is the sum of d largest values in the array, and if there are fewer than d elements, then sum all of the elements in the array as well. Yeah. So thanks for participating in this small activity. So I'll move on to pattern recognition. Pattern recognition is another concept in algorithmic thinking that allows us to identify different patterns in problems and apply established solutions effectively. So for example, you can see over here, this sequence, we can recognize it as the Fibonacci sequence. The Fibonacci sequence will be explained in greater detail later by my teammate Kian. And hence, we can use the optimal algorithm to solve it. While real-world problems may be more complex and more involved, this serves as a useful illustration for pattern recognition. So on to time complexity. How do we measure how long a program runs? So for example, you may be thinking like we can time it either using some time library in Python. So Python has this library called time, and maybe we can also use a stopwatch, but that may be less accurate. Like regardless of the accuracy of these two methods, like there still stands some problems, which is that your program on one machine may not run in the same amount of time as a program from another machine. And some programs, it takes more or less time depending on what inputs are given in. It may scale differently. Yeah. So let's say you want to find how many A's are there in a specific string. So if you supply in a longer string, your runtime will definitely be longer, and if you supply in a shorter string, your runtime will definitely be shorter. So how then should we measure our program's runtime? How long a program can run in a manner that is machine independent and can take into account the inputs supplied. So in computer science, we have big O notation, which is a way to measure the upper limit or the worst case runtime of a function by approximating the number of operations for some given input. And in this case, our input we supply is an array or also a list, and its length is n. Hence, we represent the time complexity with O bracket number of operations in terms of n. For example, O bracket n. And we call this O of n. So firstly, we have constant time over here, or it's simply known as O1 time. So operations with constant time complexity always take the same amount of time, regardless of the input size. As you can see on the graph on the side, it's a horizontal line, and hence, no matter the size of the inputs, it will always take the same amount of time. And you can see in the code block, an example is printing the first item of the list. And you can also already think that no matter how large your data is, you are only printing the first item on the list. It's only going to take one operation. So it's going to take the same amount of time regardless how long your list is. So the next time complexity is called linear time, or O of n time. So operations with linear time complexity have their runtime scale in proportion to the input size. And you can see that in the graph, we have a straight line ascending steadily. And such operations are common for processes that require evaluating the inputs by each element individually. So for example, you can see in the code block over here, the function iterates through a list and prints each item one by one, and the time taken depends on the number of items in the list. If you double the input size, your runtime will also double. And we also have quadratic time, or O of n squared. So in computational terms, an operation with quadratic time means that the time required grows proportionately to the square of the input size. And as you can see in the graph, it shows a quadratic curve, and the curve rises steeply. So you can take the example of the nested loop inside the code block example. If the input size doubles, your runtime is going to increase fourfold, as in quadruple. And this is a bit less efficient for larger datasets. However, it can still be used for more structured and well-formed problems. And now let's talk about the two most inefficient time complexities: exponential time, which is O of 2 to the power n, and factorial time, which is O of n factorial. So with exponential time, the number of operations doubles with each additional input, and with factorial time, the number of operations grows even faster. And factorial basically means that you are multiplying all the numbers from 1 all the way to n. So sometimes when you are brute forcing solutions, you may end up with a solution with factorial time complexity, which is not ideal. And we try to avoid this because it's very slow and inefficient. Also, when we are working with big O notation, there are also two key rules to simplify it. So firstly, we focus only on the higher order term. We ignore the constant coefficients. So as you can see here on the slide, let's say we have n squared plus n plus 1. We will simplify this to O of n squared only. And we also ignore coefficients. So let's say we have O of 2n squared. We will also simplify it to O of n squared. So why do we do this? We do it because it makes it easier to compare algorithms. And the rationale is also that as the input grows, the term with the highest growth rate will dominate, and lower order terms or constants will become negligible. So you can consider the two algorithms with the different time complexities, the quadratic one with n squared and the linear one with 1000n plus 10. So you can see initially the quadratic one is faster for smaller input sizes. However, as the input size increases, the linear algorithm is faster and becomes more efficient at one point. And it demonstrates how higher order terms eventually overshadow the lower order terms in terms of the growth rate. So another example to see how big O notation can be very useful to compare two different implementations of algorithms is finding duplicates in arrays. So you can see over here we have two approaches, two implementations, a nested for loop and a dictionary-based implementation. So over here, the first method, the nested for loop, it compares each element to every other element, and it results in a time complexity of O of n squared. So for example, with 10 elements, it requires, in the worst case, 100 operations to complete the first implementation. And we can contrast this to the second implementation, which uses a dictionary. So as we look through the array, we can check if the element has been seen before. And this approach is far more efficient with a time complexity of O of n, requiring only 10 operations for every 10 elements. So it demonstrates how understanding time complexity can help us optimize our solutions. So next, you may wonder, what is the time complexity of this code block? Well, this code block, it runs in logarithmic time, or O of log n. So in computer science, specifically for big O notation, log n over here refers to the base 2 variant of the logarithm, so it will be log base 2n. And logarithmic time is represented as O log n. It means that for every step, the problem size will be halved. And let's say you have your input size n equals to 2, you only need one operation. N equals to 4, only two operations. And even n equals to 256, you only need 8 operations. So you can see that it is even more efficient than linear time because it excels by exponentially reducing the problem space with each step. And you'll see more examples regarding logarithmic time in the next sections. For example, binary search, which will be covered by Boan. So I have some examples here, and I will be launching a poll for you to vote on which answer do you think is the correct one. Yeah, so I'll give around 1 minute to solve for people to vote in this. So someone raised a hand. Like, if you don't mind, you can send your question in the Discord chat. So the data structures and algorithm channel. Data structures and algorithm questions. Yeah, so we have the highest number of votes for option C, which is the correct answer. Yeah, the side switch. Okay. Yeah, option C is the correct answer, and that is because we simplify the terms in big O notation. Hence, unsimplified this will be 0.5n, but we simplify it to become O of n. And since this is just a simple for loop, it's not n squared or log n. Okay, so what time complexity is this? Here's another example. I'll launch another poll. Okay, so I shall end the poll. Yeah, so we see that most people vote for O of log n, although there is a significant number of people as well who voted for n and n squared. So for this, the time complexity is actually O of log n. And although we see here that it's multiplying instead of dividing, the fundamental gist of logarithmic time complexity remains unchanged in that for every step it takes, for every iteration of this loop, you reduce the problem space by half. So even though this differs from the division example, its time complexity is still O of log n. So here's a third example, and I shall launch another poll. Okay, so the poll has ended, and the most number of votes goes to O of n multiplied by log n, which is also the correct answer. Yeah, so good job for those who have answered the correct answer. And for this, it is O of log n because you can see here that it goes through a for loop of n iterations, but in each of the loop, it prints high one time, and it does O log n operations inside the for loop. So hence we need to multiply n by log n inside, and hence it becomes O of n multiplied by log n. Yeah. So from the previous examples and the previous slides, like you have seen many instances where big O notation is used, and big O notations provides a way to describe how the runtime of an algorithm grows as the size of inputs increases. So it allows us to compare algorithms, predict scalability, and ultimately increase the efficiency of our programs so that our programs can run faster and more efficiently. So to put it into perspective, a computer can on average run like 500 million operations per second. But as our programs handle more and more inputs, the time taken to complete tasks can increase significantly. Hence why finding algorithms that are more efficient is essential. Lastly, it's also crucial to consider that our programs may encounter larger inputs that than we may have anticipated. Hence, finding the most efficient algorithm that can handle this in the most efficient way possible is crucial for our program as well. So over here, I have a graph of uh, the CPU operations per unit time against the input size n, and it compares 6 different types of time complexities all the way from O of 1 to O of 2 power n, which is exponential time. And you can see for O of 1 is a straight horizontal line. All the way to O of 2 power n is a very steep curve. And you can see the visible difference between each of them. And hence, you can see which one is better than the other. Yeah. However, for different problems require different solutions, and you may not be able to find a solution in a better time complexity. Let's say you may not be able to find a solution in O of log n time for a specific problem, but that doesn't mean you cannot find the best possible solution for it. And it's always about optimizing for the best time complexity. So over here, I have another statistic. Here, this time is a table. So this table illustrates the estimated maximum value of n that runs in a reasonable duration in comparison with the time complexity. So as I say this, I would also like to say that a program does not have an upper limit on how much input you can supply. You can supply any amount of input that you like to an algorithm, but an algorithm that definitely have a limit on how much is you can supply that will run in a reasonable duration, in a reasonable time, and not just go on and on and on and on. So hence we can translate the time complexity to practical terms by looking at the table which estimates the maximum size of n to run in a reasonable duration. So sometimes your program may also need to run in certain constraints that maybe in competitive programming, a lot of times they'll provide different constraints for our program. So these are crucial for designing efficient algorithms, and they can include the time limit, such as like 4 seconds for execution, the input range like between 1 and 100 or 1 and 1000 that your algorithm must handle effectively. And this problem constraints, it, it helps us to design our programs to fit the constraints that is required. And some terminologies that you may hear are also AC and TLE, which refer to all clear or all correct, and time limit exceeded. So I'll move on to my last slide. So this is just for your information. Polynomial time refers to algorithms where the time complexity is expressed as a polynomial. So O of n is a polynomial time algorithm. O of n squared is in polynomial time as well. O of n to the power of 10 as well is a polynomial time algorithm as compared to exponential or even factorial time. But however, do take note that some problems do not have more efficient solutions in polynomial time, and these problems are called non-deterministic polynomial hard problems or NP hard problems. And such problems include the traveling salesman problem and the subset sum problem. And it is widely held that P is not equal to NP, and hence these problems will never have a solution that runs in polynomial time. And this is a problem that is not this is a problem that has not been definitively proven in computer science and remains one of the most important unsolved problems. So with that, I'll move on to recursion, which will be covered by my teammate Kian. Thank you.
Good afternoon, everybody. Can everybody hear me? Okay, I would assume yes. So now we're gonna move on to the next part of the today data structure and algorithm, which is recursion. Okay, so welcome everyone to data structure and algorithm. I'm Kian, and this is my part of recursion. So basically, recursion is the process of recalling a function over and over again. So in competitive programming is a thinking technique, and this is a technique that is very important for you in order to simplify a section of code, or simplify your thinking in a problem so that you can achieve the result easier. And also a lot of the time it is also the basis for other things in competitive programming that I will go through later on in my slides. Okay, so let's get started with a very simple and famous problem called the Fibonacci sequence. Okay, so the Fibonacci sequence problem can be explained like this. So you can see here, this is the Fibonacci sequence. So the first two numbers is always 0 and 1. It will be the first and the basic, like the base cases of this sequence, which is 0 and 1, the starting point. And from the third element onward, every element will be equal to the sum of the previous two elements. So you can see here, the third element is 1 because it's equal to 0 plus 1. The next element is 2 because it is equal to 1 plus 1, and so on. So as a computing student, or not a computing student, but you are interested in computing and math, the question I have for you is, how are you going to find the seventh number in the sequence? Of course, many people can think of iteration. They can just for loop the whole way from, let's say, if it equal to 3 for I in range like 3 to 7, 3 to 8, you're gonna just that number will equal to the sum of the previous two number, and you're gonna just save the previous two number in, let's say, a variable. Then you're gonna change the variable as you go on with the sequence. But I think it's very boring, and the code is going to be quite long. And most important thing is, this is not what we are covering right now in this session today. So I want to teach you how to think of recursion for this problem. Okay, let's just have a little recap of what a function is. So a function is a piece of block of code that performs a task. You can see here in the example. So first thing you need to do is always to define the function, def. Then next one is the function name, which is what in this case. And inside the bracket is the arguments, and sometimes it's a keyword argument if you have. So what you're gonna do inside the function is you're gonna give it an action for it to do. So in this case, it's print hello. So when you are gonna print out hello to the machine. So in order for a function to work, you need to call it after on. So you can see here, function what is called later on. Okay. So let's just go back to our problem in the Fibonacci sequence. So how are we going to use recursion in this? So first one, we need to have a function called fit. So the logic behind the sequence thing of how to achieve the next element is the ith element will always equal to the I minus 1 element, and the I plus the I minus 2 element. So we can just simplify it like this. Fifth I will equal to fifth I minus 1 plus fifth I minus 2. It's very simple because the element you are calling right now will equal to the sum of the previous two elements. Then you're gonna keep calling the previous two element again to achieve the number of the previous two element. Then after everything is done, you're gonna go back to recalculate the I element using the previous element. However, this brings up a question. What if we keep going smaller to smaller and smaller number of I? What if we reach, let's say, negative? What if we reach below 0? Then how? Because at that point, you know that in the Fibonacci sequence, there's no way there's going to be a negative order of element, right? So that's when we need to have base cases, which is when the recursion function will stop calling itself. So in the Fibonacci sequence, the base cases are the first two elements of the sequence, which is fifth one will be equal to 0 because it's the first element of the sequence, and fifth two will equal to 1 because it's the second element of the sequence. So far, I think most of the things are quite easy to understand. If you have any question, you can just drop a DM or anything in the, you can just also text in the group chat, or you can raise up your concern or any queries in the Discord group. Yeah. So moving on, so far, this is how our function should look like. First one, we define the function. Then we have the function name, which is fib. Then we're gonna have the argument, which is I. So we're gonna take I from outside. Let's say we want to know the seventh element. We're gonna put I as 7. Okay. So then if I equal to 1, if we are looking at the first element of the Fibonacci sequence, we return 0. And if I equal to 2, we're looking at the second element, we return 1. Okay, if it's any number other than 1 or 2, we're gonna return how we're gonna get that number. Oh, we're gonna get that number from the previous two number. Okay, so how we're gonna find the seventh element? Let's just run through the code in our brain so that we can see how it's gonna work and how recursion is used in this case. So first one, you can have see here is the base cases. So this part, the lower part is also called the transition part, or sometimes it's the recursive phase or transition phase, anything you can call it. This is when the calculations all happen. Okay. So okay, let's start with our example, the seventh element of the Fibonacci sequence. So when Fib7 is called, it goes down all the way to here, the last line, because it's not I is not equal to 1, neither is equal to 2. So you're gonna go all the way down to here. And down here, 7 minus 1 is equal to 6. 7 minus 2 is equal to 5. So fifth 6 and fifth 5 are called subsequently. So as they are called, it's going to go back to the front. And then fifth 6 and fifth 5 are going to be checked whether they are equal to 1 or 2 or not. Because they are not, so it's going to be else again. So inside the else statement, you're going to return once again, fifth 5, fifth 4, or fifth 4, fifth 3, and keep going on all the way until you reach the base cases, which all the way until you reach base cases of I equal to 1 or I equal to 2. Okay, so when the base cases are reached, it's gonna be recalculated. Fifth 7 gonna be recalculated based on fifth 6. Fifth 6 gonna be recalculated based on fifth 5, and so on, so on, so on. And after everything, then you're gonna have the number of fifth 7. So here's an illustration for you to understand it better. So you can see here, it looked like a binary tree, which is in this case. So fifth 7 here will be equal to fifth 6 plus fifth 5. Fifth 6 will equal to fifth 5 plus fifth 4. Fifth 5 will equal to fifth 4 plus fifth 3. And it's keep going on all the way down to the lowest notes you can see here. It's fifth 2 or fifth 1, fifth 2, fifth 2, fifth 1. And these are all the base cases. And you're going to have the integer number from these base cases. And you're going to work back up to find the value of the seventh element of the Fibonacci sequence. So this is the order you're going to look when fifth 7 is called. And when fifth 7, and here in this case, fifth 7 is what we're looking for. But let's say if we're looking for fifth 8, fifth 10, fifth 12, all of them are also possible using recursions. However, you also need to bear in mind that for this specific problem of Fibonacci sequence, recursion is not actually a very useful way of tackling this problem because it's very slow. In this example we're showing you right now, the time complexity for recursion is O2 to the power of n, which n is the number that we are looking for. Let's say in this case for 7 is O2 to the power of like 7, because we have to do a lot of calculations, and after every number we need to calculate like the calculation. We need to calculate the previous two number, then from that two number we need to calculate like four more number, and so on, so on, so on. So it's quite not a very effective and cost efficient way to solve this problem. It is a good way to start with recursion. So if you are wondering, then how are you going to use recursion for this problem? There's something called dynamic programming, which is basically just recursion, but with a little twist of having memoization. So if you use memoization for this problem and you use an approach called bottom-up dynamic programming, you will be able to solve this problem in a faster time, in probably log n if I'm not wrong. Okay. So far you know about recursion. You understand what recursion is through the problem of Fibonacci sequence. So we're just gonna sum up what we have learned so far. What is recursion? Recursion. So recursion is the process in which a function calls itself directly. So you can see if in the example of the fifth function, it keep calling itself. Fifth 7 call fifth 6, fifth 5, fifth 6 call fifth 5, fifth 4. So that's how it works. It keep calling itself over and over again. Recursions usually require three steps. First one is to find the endpoint, the base case. for the Fibonacci sequence is when the first and the second element of the Fibonacci sequence are called. So then the recursion will stop and we're going to start backtracking. Next one is we need to know what's the recursive pattern. So how are you going to find the next element in the Fibonacci sequence? The Fibonacci sequence, the next element equal to the sum of the two previous number. In some other way, let's say in a tree, you need to go down the tree in a way that you need to iterate through all the adjacent nodes of the other nodes or the child nodes of the parent, something like that. So you need to know in what order, in what pattern are you using for this recursion. And last but not least, very important is you need to ensure that recursion will definitely end, because most of the time, if recursion will not end, right, it will lead to sometimes it may lead to like TLE, which is time limit exceeded, because the the looping, the calling itself directly will never stop. So you will just go on indefinite in like for not a certain number of time, like till forever. So you need to ensure that it will end, recursion will end. Yeah. Okay, so when to think of recursion, since recursion is this very like complicated thinking way to solve some of the issues. So when should I think of recursion? Okay, so let me tell you, you should think of recursion when you see, let's say, a big problem. You are able to find the pattern in the big problem so that you can divide the problem into smaller chunks of the same problem of the same nature. So let's say Fibonacci sequence, right? You can see the sequence, you can see the pattern is the, the number will always equal to the sum of the previous two number. Oh, that's a sequence. That's the nature. So they all have the same nature. So uh you can similar like you can make them because they are so similar. So you can group them together to make it a process. And you can divide a big problem into smaller problem, and you get the value from the smaller problem to go back to the big problem and solve the big problem. So that's what recursion, that's when you should think of recursions. Yeah. Next one, many time recursive is a must over iterative, let's say for directory traversal in Python, which is something that we will not be covering today due to a time limit. But it's, let's just know that recursive make your code way neater, because it's very useful in a lot of the way that you present your code, right? In a lot of the way your logic is present in the code, it will make the code way neater. You don't have to use explicit looping all over again. Then you have to, like, let's say for the Fibonacci sequence, you don't have to have variable to keeping track of like what's the two closest like previous elements. You don't need that. With recursion, you just need three for line and you can already solve the problem. Okay, so what are some uses or implementation of recursions? So first one you can see here, I have already popped it out, which is dynamic programming. So dynamic programming, as I have mentioned before, is just recursion with a bit of twist in memorization. Memorization is basically you are remembering the states of some of the data without the need of recalculating them. Okay, I know it's a bit like complicated for you guys to understand right now, and we are also not covering dynamic programming in much conference, but uh, I'm in Python. I'm pretty sure that in Python, dynamic programming with is just it's quite easy to implement. Let's just say you think already of the recursion way of solving the problem, you can just memorize it. You can just have another variable or like another vector or another list or something to to store all the number that you don't want to recalculate to prevent the the huge amount of recalculation you may use. Okay, so come back to our own recursion slides. So divide and conquer is also another technique. When you have a big problem, you divide them into smaller problem of the same nature, and the same mindset of recursion. So recursion is very helpful if you want to think of divide and conquer DP at the same time. DP is dynamic programming. So recursion is the basis for these two techniques that are very important in DP and algorithmic thinking. Okay. Then next one is sorting techniques. So many sorting techniques use recursion to sort effectively. Let's say like quick sort or like heap sort. All these sorting techniques, they have a way, an algorithm that use recursion or use dynamic programming in order for them to effectively sort a list. Okay. Next one is tree and graph. So these are the very important areas of CP, which is comparative programming. Recursion provides an efficient graph and tree traversal. So let's say you have DFS, you have BFS, which is like depth first search or like breadth first search. If you want to go down to all the elements of the tree, right, you need to know what order are you looking for, what order are you looking, what node are you looking for. So in these circumstances, recursions can be a very effective buddy in these circumstances. Okay, moving on. We're gonna have a small problem right now for you guys to start like thinking in a recursive way. Okay, so first one, we're gonna have the dash row problem. Let me sum it up for you. So dash row is basically the problem of, oh, you have n dashes and you're gonna roll them all. Each of these dashes have x sided. You have to show every possible rows that sums up to c. Here that some of the constraints of the constraint is like to ensure that the your code, even though it's in Python, right, it can still be run because it's not that slow. Okay, so it just like uh to limit your coding from like going too long and solving the question for too long. Yeah. So you can see here one of the example for this question is when n equal to 3. So you are rolling 3 dice and each dice have 4 faces, and you need to find how many possible rolls, how many different combinations are there where the faces of the dice will sum up into 6. Okay. So you can see here there are some examples. 2 2 2 2 1 3 4 1. All of these sum up to 6. Okay. So many of you, I'll give you guys some minutes to think about this problem first. Let's say about 3 to 4 minutes. We're gonna go back at 4 and we're gonna discuss this problem. And I'm gonna tell you guys why you guys shouldn't use iteration in this case. And recursion is actually a better approach to this problem rather than iterations. Okay, so we're gonna go back at we're gonna start again at 4. Okay, guys, welcome back. So we're gonna discuss the problem right now, dice roll problem. Some of you may think like, oh, I can just iterate through all the faces of the dices. Then I'm gonna keep track. Oh, maybe for this sequence, I'm gonna have one number, gonna keep it in a list. Then next one, I'm gonna keep another one in another list. But when you do that, right, it's gonna have a problem of keeping up with too many variables, keeping up with too many lists, and you're going to be sometimes it may cause to like something like stack overflow and things like that, which is quite not a good practice in competitive programming as well as in any type of like programming as well. So I'm going to show you the conventional method of looping. This one you can see here. We're just going to loop through all the faces, through all the dices, and then loop, and then we're going to have the answer like how many of them how many of the combinations are going to sum up to the desired sum that we are looking at. However, there's a problem of we cannot backtracking the dices because yeah, I told you we have to have a list to solve all the possible like combination and things, but it's proven to be quite difficult if you want to use iterations in order to track back the dices because sometimes you have to keep a lot of the value in check. You have to put a lot of variables. So however, there's a advantage of recursions in comparing to like let's say iteration in this case because recursion actually allow you to be able to track back the dices in a very like effective way and not very like long code. It's not very complicated to think about and it's also very easy for you to understand. Okay, so we starting things first with how are we gonna recognize the pattern? So what are we gonna do in order to achieve the desired combination? Like we just need to like print out all the combination, right? So how? So first one, we need to know that we have two tasks for this problem. The first task is to find a combination of dices to make up the sum. Yeah, we need to know what combination, what sum. Okay, so we need to know them. Then we need from that one, we need to trace back on which dice will give what number in order to make up the sum. So we need to track back in order to find the numbers on the dices, make up the sum. Yeah, that's basically what it just in a different words. So from these two tasks, right, which one can you be solved using recursion? Which one can be solved using like let's say just traditional loop, like explicit looping? Which one? Of course, the first one can be solved using recursion over rolling dice. So we just wanna try that we are rolling dice every time. We're just simulating the fact that we are rolling another dice. Then when we roll the dice, right? Because we are not actually rolling the dice, so we need to take in we need to take into account that we are looking for all the faces of the dice. So we need to be prepared that we are looking through all the faces of the dice and all those faces. We just need to like put them in check because anything is possible for this task. Any combination may be possible to make up the sum that we are looking for. Okay, so the second task can be solved by iterations over components. So we just need to iteration over all the thing that we have rolling so far. So let's say we roll one dice, we get one number, then we keep rolling the next number, we keep rolling, right? Then after every of the rolling, when we have only one dice left, we just need to track back in order of all the roll we have done so far in order to know that what's the combination we are looking for. Okay, so let's jump into the base case and the recursive case for this problem. So first one, the base case is when the is the last dice roll. We just need to iterate over all the possible values before returning the all the combinations and things like that. Because like when we only have one phase, after we only have one dice, after that dice is rolled, right? We don't need to roll any more dice. So that's gonna be the base case of our equation for simulating the the process of rolling the dice. Okay, then the recursive case is gonna be to loop over all the possible values of the dice. Because as I said, anything is possible when you roll a dice because you are not actually rolling the dice and you have one number. When you are simulating the full process of your rolling the dice and in any different universe, you can have any different number. So let's say this universe you get three, but the other universe you get four, and you have to take into account of all those number together. Okay, so next one, we just start with the coding part of this problem. So of course we need to have a function called roll because we are simulating the rolling of the dice. Then next one just need to define the function. We have the function name, we have the argument, everything. So in the function, we take two variables. First one is the depth. So how many rows are left to be made? Initially, the n rows, because initially we need to make n rows of dices. So that should be started with n, and total, which is the sum of the rows so far. Okay. Next one is we're just gonna put all those variables, all the arguments inside the functions. Yeah, because we need to keep track. We need to have them in to keep track of what row are we making, and what's the total so far. Okay. Okay, next one is the base case. Very simple, as I just said before. The base case when it's only one dice left. We are rolling the last dice. So we just need to iterate through all the phases, all the possible phases. You can see here why is for I in range 1 to phase plus 1. Because as you learned from yesterday, right, for loop is the first number is included in the range, but the last number is not included. So when we are checking for I in range 1 to phase plus 1, right, we are checking from all the number from 1, 2, 3, 4 to phase instead of phase plus 1. So we just iterate through all the possible values of the phase of the dice. And if any of those value sums up current with the current total value from all the dices before and equal to C, which is the desired sum, we're just gonna record that dice down. And after that, we're just gonna need to print all the previous dices out so that we have one combination of everything. Because then after we have one combination of everything, we just need to return. We just need to stop the process. Because from this moment onward, we are not going to make any more rolling of dices. We have already our combination and we just need to stop. Okay. So we return from there. Next one is the recursive case. Recursive case is when you are simulating the fact that you are rolling a dice. So a bit similar to the previous case of the base case, right? In recursive case, you also need to simulate that, oh, you can have any value of the dices on your combinations. So this is what you do also for I in range 1 to phase plus 1. You just need to record down the value of the number you just roll right there. So using in a, let's say in a list, this one. So n minus step is actually we are recording what row, what's the sequence of the row we are doing right now, like what row are we making right now. So let's say if it's the first row, then that will equal to n, right? So it will be that is 0 will be equal to I, because in Python we're using zero index, so that's why the first element will become 0. Yeah. So we just need to have that to keep track of what number are we, what's the row order are we doing right now. Okay, next one, we just need to roll. We're gonna do recursion again because we need to roll again. That minus one, which means like, oh, we have row one row, we just did one row. So we need to roll one more. Or we just need to roll that minus one time. Let's say first one, you started with that equal n, right? After you make the first row, n will minus one because you only need to make n minus one more rows. So that's basically how you have that minus one in this case. And total plus I is basically because the total start with 0 and you just roll a dice of one, let's say of I, right? Maybe I is like 3 or 4. So the total now is will be 0 plus that number you just roll. So 3 or 4, which we should be 3 or 4 in this case. Yeah. Don't worry if you cannot catch everything so far. After this, I'm gonna just flash out to you the final code of everything. Okay, so that's basically the logic behind how we're gonna use recursion in this problem in order to trace back everything, in order to simulating the fact that you are rolling dices and you're looking through all the possible combinations of the dices and of all the values that can be rolled. Okay, so this is the final code that I promised you I will have. So first one, as I said, we need to have a function called row. We're just gonna initiate a function with a argument depth and total. Depth gonna start from n because we need to row n times, right? So it's gonna start with n. Then total is gonna be 0 because so far we haven't rolled anything. So the total will be 0 because we haven't have any number in the combination yet. Okay. So next step on the base case when is the last dice roll. So for just copy everything I have told you so far. When it's 0, then you're gonna just gonna when it's 1, then you're just gonna iterate through everything. Yeah. Then if it not 1, if it not the last dice roll, you're just gonna iterate through all the other phases that's possible of this current row you are doing. That's what I say. Yeah. Yeah, so you after that you're gonna call again. You're gonna call for the next row because you have already rolled this row, so you're gonna call for the next row. And after the next row, you call for the next row, and keep doing like that. And subsequently, you're gonna reach when it's the last row. and you're just gonna in out everything. Okay, that's the logic behind this dashrow problem. Okay, so anyone can tell me what's the time complexity of this one? You can send in the you can send the Discord group chat if you are like curious and you want to like consolidate. Okay, never mind. Then let me just tell you guys that for this problem, right, the time complexity of it is actually O n multiplied by the face of n. So basically, this is the number of time we are simulating the process of rolling the dice. And because we have n rows, so you're just gonna multiply it by n. Because face to the power of n is like we are taking care of all the possible value of face. We are just gonna go through all the faces values in time. But it need to be exponential because it's like stacking up instead of multiplying. It's a bit complicated. And the total will be like O of 10 to the power of 5 or something. It shouldn't be 7 because I just checked the constraint again. It shouldn't be 7. Yeah. Okay, so that comes to the end of my recursion part. Recursion part. So I'm gonna move on to the next part, which is data structures by Limbo and
Okay, hello, welcome to the data structures portion of this workshop. So what are data structures? Data structures are storage containers that find a way to organize data that we care about so that we can perform operations on that data a lot easier. So the first data structure we have is a deck. So what is a deck? A deck is an indexable data structure that allows you to remove or add items from the front or the back of the deck very easily. All of these operations on the deck take all one time, which, as Lucius mentioned earlier, is a very good time complexity. A deck can be also thought of as a big brother to the queue data structure, which is very similar to a deck, just missing a bit of functionality. So this is the basic deck syntax in Python. To call the library, we use from collections import deck, and to declare an empty deck, we use dq equals to deck open close parentheses. In this case, I am declaring an empty deck called dq. So to pop and push items from the left side of the deck, we use dot append left to append items to the left side of the deck. And we use dot pop left to pop the leftmost item of the deck. And to do these operations on the right, we use dot append to append an item to the right of the deck. And we use dot pop to pop the rightmost element of the deck. So this is the visualization. So first of all, use from collections import deck and declare an empty deck called dq. As you can see, we have this here. Next, we will use dot append 1. And as you see, this will append 1 into our empty deck. Next, we will use dot append left 2. Notice how we actually appended the 2 to the left of the 1. That's because dot append left appends to the left side of the deck. Next, if we wanted to append something to the right side of the deck, in this case 3, we would use dot append. As you can see, 3 has been added to the right side of the deck. So if we wanted to pop the leftmost element, which in that case was 2, we would use dot pop left. As you can see, the 2 is now removed. And if we want to pop the rightmost element, we would simply use dot pop. As you can see, it popped 3, the rightmost element from the deck. So some of the other functions are len dq, which has a time complexity of O1, reversal, which is deck name dot reverse open close parentheses, which has a time complexity of ON, and indexing, which has a time complexity of O1. This is exactly the same as normal list indexing in Python. So how do we use a deck? So I'll present this abridged problem statement, and you can use this link to access the problem on Codebreaker. So we have to handle three operations. Operation 1, someone with a value of x joins the back of the queue. Operation 2, the person at the back of the queue decides to leave the back of the queue. Operation 3, the person at the front of the queue leaves the queue. So notice how most of these operations only require us to remove or add people from the front or the back of the queue. Therefore, we can actually use a deck for this question. And this is the implementation. Please note that this solution only gets 99 points because Python is just way too slow of a language to get the last 1 point for the full solve. So here is the practice problem. This is the problem link. If you want to search it up, its name is Smurf and it is on Codebreaker. Okay, you have 10 minutes to solve this and I'll go through it after. Yeah, please note that you'll be given an extra 5 minutes to 10 minutes to attempt this problem. Okay, due to some time constraints, the time allocated for the problem will be ending now. So here's the abridged problem statement for this problem. We have n integers and we want to arrange them in a row. So what we'll do is we'll perform this operation n times. We'll append the ith integer in the row, in the array we're given, to the front of the row, and then we will reverse the order of all the smurfs in the row. What we have to do is output the row of integers after all n operations have been completed. So as a beginner, this problem is not too easy to solve. So we'll need to put on our thinking caps a bit. So let's say we have the row of integers 1, 2, 3, 4, and 5. Obviously, if we reverse it, it will be 5, 4, 3, 2, and 1. So the essential observation is, if we reverse the row, only the side that we append elements to changes. I'll illustrate this with an example. For example, if we wanted to flip the row 1, 2, 3, 4, and 5, initially we were appending to the left side or the side that had a 1. But if we reverse it, all we're really doing is changing the side that we append to from the side with the 1 to the side with the 5, or more aptly put, we're changing the position that we append the element to from the left side to the right side. That's all we're really doing when we reverse the row. And if we need to append elements to both sides, then we can use a deck. So this is the sample code. This is the input specifications and our variable. So this loops n times, and we will basically take this final variable. If it is divisible by 2, we will append the ith element to the right side. But if it's not divisible by 2, we will append the ith element to the left side. What this will basically do is simulate the swapping of sides inside the code. Now you might ask, what is the use of the final variable? This will determine the final side of the row. Since we cannot really track I outside the for loop, we need this variable to tell me whether I need to output it starting from the left or whether I need to output it starting from the right. So this we do just this. If final modulus 2 equals to 1, we just print normally. But if final modulus 2 equals to 0, which means it's on the other side, we have to reverse the deck using deck.reverse, then print it. But you might ask, why can't we just reverse every time? So think of it. We're using for I in range n, this is On. If we reversed it every time, we'd be reversing, which takes On time, n times. This will give us n times n, which is On squared time complexity. This simply isn't good enough to solve the problem within the specified time limit. So here are the use cases. Now, when would I use a deck over other data structures? You use a deck when you need to perform both operations on both sides of the container. So next, we have a 2D array. Let's say we're presented a grid of integers and we have to find the coordinates of all 3's in the grid of integers. But how do we even take a grid of integers as our input? Well, the answer is through a 2D array. This is a 2D array. Well, you might ask, what is that? Actually, it's just this grid of integers right here in a usable format. So let me explain. A 2D array essentially stores arrays of arrays, or it is essentially an array of array. As you can see, we have one array here, another array here, and another array over here. And each subarray basically represents a row in the grid. As you can see, this first array is row 1, this second array is row 2, and this third array is row 3. And each item in these respective subarrays represents the item in row Y, column X. For example, this item right here would be the item at row 1 and column 1, whereas this item over here will represent the item at row 1 and column 5. Notice how this is actually very similar to getting values from the Cartesian plane. That's the whole idea behind a 2D array. It simulates the Cartesian plane so that we can actually use it to write programs. So how do you read values from a 2D array? We essentially use indexing firstly on the overall grid array. This will return the row. Next, we will use indexing on that row to return the item at row Y, column X. For example, this is the first round of indexing. This is the Y value or the row number. And next, we have the X or the column number. So this is how you input a 2D array in Python. So this basically means for each row, and for each row, we have a temporary list. Next, for every item in that row, we will append it to the temporary row array. Next, we will append that row array to our overall grid. This will repeat over and over again until all rows have been stored inside the grid. So to search through a 2D grid array is actually very similar to inputting it. We simply iterate over every row, checking every value in that row, and then moving on to the next, repeating until the whole grid has actually been searched. So this code means for I in range H, which means for each row in the grid, and for Z in range, len, and grid I, which is the row number we're currently at. What this basically does is it iterates for every row, and for every row, we iterate through every item in the respective row. And then this is just a conditional statement to see if our grid, if our current element is the item we're looking for. You'll probably be modifying this depending on the problem you do. So here's a visualization of the traversal algorithm. Let's say we have this grid and we want to traverse through it. We'll start at row 1, which is our current row, and we'll start at column 1, which is our current column. As you can see here, the algorithm actually moves through every single item in the row until it reaches the last element. And after that, it actually moves on to the next row. And as you can see, the column pointer has actually just moved over to the start all over again. Now we just repeat this over and over again until every row and every column has been searched. So how do we actually use a 2D array? I'll use this sample problem. You can enter in the URL now if you want to follow along. So the abridged statement is that we have a 2D array of either pavement or penguin. You have to find the coordinates of the one pavement string in the 2D array. So this is some sample input. As you can see, we have a 2D array that has five columns and 4 rows. And you'll see that pavement is right over here. And we will just output the coordinates. As you can see, it's in 0, 1, 2, 3, column 3, 0, 1, 2, column 1. Note that this 2D array is actually 0 indexed. Notice how that we can just search every value in the array, as checking every value will actually take OHW time, which in the worst case is only 900 because H and W respectively, they are capped at 30. And to search through the array, all we really have to do is traverse it to find the coordinates of the pavement value. So this is the sample code. If you look carefully, you'll actually notice that it's just the 2 templates I showed you earlier, but just glued together in one single block of code. As you can see, we have our input and we have our traversal right here. Well, I would give you a practice problem if almost all the 2D array questions on Codebreaker are pretty hard, or they just use graph theory concepts. So just store this information and it'll probably help you quite a bit. So next we have the priority queue. Okay, so we just got off DEX. Now what's this? A priority queue is actually a unique kind of queue that always keeps the element that is the largest at the top. Take, for example, if we try to push 1, 5, 3, and 2 into a priority queue. The priority queue would then be 1, 2, 3, and 5. Notice how the 5, which is the largest element out of our arrangement here, is the one at the top of the priority queue. This is because the priority queue actually automatically sorts it by how large the element is, or its priority in this case. So here's the basic syntax in Python. So to import the library, we will use from queue import priority queue. In this case, I will be making a priority queue name queue. To declare priority queue, we just use priority queue name equals to priority queue open close parentheses. Please note that in the declaration of a priority queue, the P and the Q of the word priority queue both have to be capitalized. So how do you add elements to the priority queue? We will use q.put, and in the parentheses, we will put the item that we want to put. This queue can be swapped out for the name of the priority queue you want to use. An item is the item that you want to append into the priority queue. To delete elements from the priority queue, use .get. This get function is a bit unique because this function actually just deletes the smallest item and returns it. So if I use print q.get item, it will not only remove the top, it will not only remove the top, but it will also return the top item. Please note that there is no input in the parentheses. Sorry for the slight mistake in the slides. So here's a visualization. First, we will import the library as always, and we will declare an empty priority queue named Q. So as you can see, this is our priority queue and it's currently empty. First, we will put the item 2 into the priority queue. So now 2 is the only item. Next, we will put 3. As you can see, 3 is automatically pushed in front of Q because 3 has a larger priority than 2. In this case, it's actually just larger than 2, so it's put in front of 2. Next, we will use q.put 5. Now, 5 is higher than both 2 and 3, which means it's the item with the highest priority. So it will automatically be put at the top. Next, we will use q.put 4. What you'll observe is that 4 is actually automatically slotted between the 3 and the 5. This is because when you use put, the put function automatically puts that element in the order of priority. This will make sure the priority queue is perpetually sorted in terms of priority or how large or small the element is, depending on what you want. So this is our current priority queue. If you use .get, you will see that 2 is actually popped. Why is 2 popped, you ask? It's because get actually pops the lowest item from the priority queue. So it went from 2, 3, 4, 5 to 3, 4, 5 because 2 was popped from the priority queue. But what if we actually want to be popping the top element with get? Because that's what most of priority queue functionality is meant to do. Well, then we have to use a priority queue of inverted values. Since priority queue in Python by default is a minimum priority queue, which means that the minimum item is always at the top. Using negative values makes the positive values actually seem lower and the negative ones seem larger internally inside the computer system. For example, if I try to append 9 and -6, 9 will actually be changed to -9, and 6 will actually be changed to +6. Now, if I use get, it would pop the correct element, which is 9, or in the priority queue, it would be -9 from the priority queue. If you wanted to pass these elements outside, once you've retrieved it with .get, you simply just have to invert the values and use them however you want. This all makes it so that get works like it would in a max priority queue. Okay, all that syntax is really cool, right? But how do we actually use a priority queue? So This is the sample question I will be going through. Feel free to type this URL in or just search up party_NOI on Codebreaker to find the problem and follow along. So the abridged problem statement is we have n friends and we have n divided by 2 seats because every friend needs to sit 1 seat apart due to COVID-19. Each friend has a certain satisfaction value from going to the party. We have to find the maximum total satisfaction value we can achieve from inviting the friends to the party. We don't necessarily need to invite n divided by 2 friends. We just have to maximize the total satisfaction. But how do we get the top few people? We can use a priority queue, since the priority queue arranges the elements in a list based off of their priority, which is greatest in our case here. So the rest of this question is quite a simple algorithm. First, we will initialize a final answer variable. I will name it res. We take the top value from our priority queue and add it to our current total, and we pop that value from our priority queue. This can be easily done using get, because get does both of those things in one function. Next, we will weigh our current total against the result, and we will take result as the maximum between result and the current value. We repeat this n divided by 2 times because we have at most n divided by 2 seats. Note that if n is actually an odd number, we can actually fit one more person in. But why do we need a result variable? Why can't we just return the current value in our array? We need a result variable as we can actually invite less than n divided by 2 people. Maybe the last few people actually have negative satisfaction values, meaning they do not want to go to the party at all. Then it'll actually be more optimal for us only to take the positive values. What the result variable is actually a variable that takes the maximum at every stage. So that if the current satisfaction ever drops, i.e. we put a negative value into our current, the answer we have recorded is still the maximum possible satisfaction value we can get. So here's an example to illustrate this. Let's say our initial array is 5, 3, 2, -1, 4, and 5, and our n equals 6, n being the size of the array. Now we will just put all the values into a priority queue. The priority queue will look like this. As you can see, it's automatically sorted. Note that this is actually the top of the priority queue. Now we take the top n divided by 2 equals to 3 elements from the priority queue. So we have the top 3 values, and our sum would actually be 5 plus 5 plus 4, which is actually the maximum possible satisfaction value we can get from inviting our friends to the party. So this is the sample code. As you can see, we just do the basic input and priority queue things. Next, we will use, for every item in our input array, we will actually put it into the priority queue. Note that we have to put negative item. Since we are trying to use a max priority queue, we actually have to inverse the values using minus in front of those variables. Next, we will store the amount of iterations we do. We use floor divided by 2 because the amount of iterations can never be a floating point number, and if the number of iterations or n is actually odd, the for loop will bug out. That's why we use n divided by 2. Next, we'll check if n is actually an odd number by using n modulus 2. If n modulus 2 is 1, which means it's an odd number, remember that we can actually have one more person that we can invite to our party. Next, we will initialize our result value and our total value. Next, we will, for I and range iterations, which means we iterate iterations times, and we will get the top value from the priority queue and add it to our total. Next, we will weigh our result with res. The reason why I use negative total here is because total is actually just the sum of the inverse values. To bring it back to its normal state, I will have to inverse the value. So we will take the maximum of that and the result. Note that this is commented code. And after that, we will print the result value. Note that I do not think apps is really necessary here, but it solves the problem. So here's the practice problem that you can do. But a very important notice is that you should just try and get subtask 2 in Python. There is a solution that full combos the whole question in Python, but it is not using this module. It uses a different module. So all you really have to do is solve for the subtasks. Okay, you have 10 minutes. Your time starts now. Oh yeah, if you have any questions about the problem, you can send it in the Discord channel. Okay, the time allocator has ended. Now I'll explain the problem. So the abridged problem statement is we have a row of girlfriends ranked by height from 1 to n, 1 being the tallest and n being the shortest. From all I, for all I from k to n, we have to find the k shortest girlfriend among every element from 0 to I. If you think hard, we might observe that the only thing we need is a priority queue of size k. So the algorithm works by basically maintaining a priority queue of size k, and every iteration we just take the last one of each query. Then every iteration we just output the last one of each query. So this is the sample code. As you can see, first we import SYS, and most crucially, we import priority queue. Next, we will declare n, k, and k, and map the input to these variables. After that, we will import or make a priority queue called pq in my case, and we will input our array. So for every I, from I to n, we will put the ith element in the range, in the current priority queue. If the priority queue size ever goes above k, we know that we will not be able to get the kth shortest with priority queue functions, as we cannot straightforwardly use indexing on a priority queue. So we will have to pop the item from the priority queue using pq.get to bring it down back to size k. So if the size equals to k, we will first initialize a variable called current, or car in this case, and we will use pq.get to assign it to this car variable. Next, we will print it, and we will actually put it back into the priority queue. But why do we do this? First of all, since we cannot explicitly get the tallest or shortest from the priority queue, we will just have to use the get function to get the value and pop it out. We assign it to a variable, and then we simply pop it back in. And if it's k plus 1, we will simply get the second highest by using this method. Note that this solution is not fast enough to work in Python. And by work, I mean fully solve the entire question, because Python is quite a slow language. So when would I use a priority queue over just appending the item to a list and sorting it every time we append? Firstly, if we were to append an item and sort it every time, if we were to do it n times, we would actually observe that it will take O n squared log n time complexity. Why is this so? Because sorting requires O n log n. It's quite consistently O of n log n for every language's sorting function. If we keep repeating it over and over and over again n times, the total will eventually just sum up to n squared log n, which is, while there is a log n, we still have that n squared, which makes it quite a bad time complexity. Next, we will do it when we just consistently need the top element. Since priority queue insertion is actually O log n, it's actually more efficient than sorting every time. So if you just want the top element, we can simply just use a priority queue to retrieve it very fast. Note that, again, if you're trying to retrieve the largest, you have to invert the elements of the priority queue inside of Python. But if you just wanted to get the smallest, you don't have to make any changes at all. Next, we will be going on to algorithms. For this segment, I'll give you a 5-minute break before we go on to the next segment.
Okay, hello everyone. Now we'll be moving on to the next and also last section for this workshop, which is on algorithms. An example when an algorithm is used is when we search for Hatsune Miku in a sorted array of Hatsune Mikus. Also happens to bring us to our first algorithm, which is binary search. In this section, we'll be searching for Chaewon in a crowd. But before that, you might be wondering, what is binary search? As the name implies, it's a search algorithm and it's used to find the position of a value that you want to find within a sorted list. It works by reducing the number of things that you have to look through by half each time until you find the value that you want, or until there are no more things within the list to search through. We can decide where to halve the list by comparing the target value with the current mid value, which is the middle value in the list. For binary search, the time complexity is O log n, which is relatively fast. So what's the difference between binary search and complete search? Complete search is when you look through every item in the whole list to find the value you want. Here's an example. Let's say I had go back to the previous. Let's say I have this K1 photo card and it's hiding behind the integer 6, and we have to find it within a box. So in this case, as I mentioned before, based on the definition of complete search, you have to look through the entire array to find where the number 6 is, and this will take O n time. It's still okay and it's still quite fast, but as mentioned before, binary search is O log n time, which is faster than O n, so we should choose binary search instead. So let's say I have this box of every item within, and Cheon is somewhere inside this box. So what I have to do is firstly, I have to get rid of the Kirby on the top, then the football, and then the rugby. And I realized that Cheon is still not inside. So I continue finding by getting rid of the backpack and the teddy. And then I find Cheon at the bottom of this box. So over here, I've represented each item in the box using a number. Integer 1 represents Kirby, which is the top item in the box, and Cheon is represented by integer 6, which shows that she's at the bottom of the box. And this is how it looked like in the list version. And the arrow points to where Cheon is currently. As mentioned before, binary search is where we divide the length of a sorted list in half to reduce the number of things we have to search. Over here, our middle value is between 3 and 4, so it's around 3.5. Our first half will include anything below 3.5. In this case, it's 1, 2, and 3. Similarly, for the second half, anything above 3.5 will go there, which in this case is 4, 5, and 6. We then compare the mid value of 3.5 to our current value in 6. As 3.5 is lesser than 6, we can cancel the first half. As all the values in the first half is less than the mid value, we know that the first half is guaranteed to not be where the target value, which is 6, is. Thus, we can cancel it. And this makes our new midpoint in the middle of our second half. As we also have an odd number of items in the second half, we can put the extra item in the new first half. Next, which will look something like this. Our new mid value is now around 5.5 as it's between 5 and 6. As 5.5 is still less than 6, we can also cancel the first half. And now we're left with the second half. And inside the second half is the value we're looking for, number 6. And with that, we have found Cheon and our program can end. So when you do want to implement binary search, these are some of the conditions that you have to consider. Firstly, your list must be sorted before using the algorithm. Your list must also be monotonic, which means it can only be increasing or only increasing, or only decreasing, which is similar to the linear graph at the bottom right-hand corner. As for now, that's all you need to know, but usually we use binary search when we have fewer inputs and we need to find values in the list more often. So why do we use binary search? As seen in the previous example, binary search is way faster than complete search. This is helpful when we do have a larger set to sort through. An example of a larger data set would be, for example, your hard drive, etc. Binary search is also more efficient than other searching algorithms with an O log n time complexity. This could include interpolation search or exponential search. Just a quick summary of exponential search is so we can better visualize why binary search is better. So for exponential search, imagine you're looking for a toy in a really big box, but you don't know where it is. First, you start by jumping to different spots in the box, getting further and further each time. For example, you start hopping by 1, then 2, then 4, and so on, until you find a spot where the toy might be. Then you use binary search in that range where you think the toy might be. And for now, that's it for exponential search. I'm teaching you that in this workshop, but it's just for better visualization. However, binary search also has its disadvantages. Firstly, you need to resort your list every time you add a new input. Secondly, you can only use binary search on one list at a time, and you can't perform binary search across two different lists concurrently. Yes. And next. So here we have an example question from the code. I suggested it's this question as it focuses purely on binary search topics like sorting. So let me just read out the question. It says, given an array of integers nums, which is sorted in ascending order, and an integer target, write a function to search target num. If target exists, then we return its index. Otherwise, we return -1. You must write an algorithm with O log n time complexity. So firstly, I have bolded all the variable names so it's clearer to start the question. Then just to break down the question a bit. So what it's basically trying to tell you is to find a value that they give you within a list. Find it, then we return the position of the value. Else we return -1 to indicate that the value is in the list. By looking at the time complexity, we should already think of binary search as a possible option too. Um, I'm sorry.
Sorry everyone. We will have a 5-minute break to settle some technical issues. Sorry again. Sorry again for the inconvenience. the workshop will restart at 5:25. Sorry for the inconvenience. Again, sorry for the technical difficulties. We'll be moving on with the workshop now. So this example problem is actually just the lead code problem on binary search, which is basically given an array nums, which is sorted in ascending order, and an integer target. Write a function to search for where target is in nums. If target exists, then we return its index. Otherwise, we just return -1. We must write an algorithm that will search for target in O log n time. Please note again that nums is sorted. So nums is sorted, you have to find target. You can put 2 and 2 together and boom, you get binary search. So this is the sample solution in Python. So firstly, we'll declare a left pointer, or in this case, I will call it pointer, and a right pointer. At first, these two will be set to the leftmost end of the list and the rightmost end of the list. These left and right pointers basically symbolize the minimum, the leftmost element and the rightmost element of our search range. So next, we will use this while loop, while left under equals right. Why do we use left under equals right? Because if left ever goes over or left ever goes over or equal to right, it means that there's no elements that we can search anymore. Next, we will use this mid equals left plus right, floor divided by 2. Why do we use floor division? This is because indexes in an array cannot be floating point numbers. That's why we use floor division to fetch the mid. So if nums mid equals to target, this checks if the middle value is already the value we're looking for. If it is, then we just return mid as the index of the target value. And if nums mid under target, since it's a sorted array, if the value of mid is actually underneath target, we know that any item that is under mid is actually will never contain target. So we will disregard that half completely and set left to mid plus 1. Why do we use mid plus 1? Actually, it's because we already know that nums mid is not the target. So we don't have to include that. That's why you use plus 1 to skip over that value. And else is basically if nums mid is over target. If nums mid is over target, we know that any value to the right or above mid will never have our target value. Thus, we use right equals mid minus 1. This basically cuts the search value in half. Why do we use mid minus 1? The same reason as why we use left equals mid plus 1. It's because we already know that right isn't the item we want. Therefore, we can just disregard it from the search query, from the search range completely. And eventually, if we keep using this over and over again, we will eventually get a mid value that will be equals to target, or you will eventually get the index that points to target. But if this never procs, we will just return -1 to show that we have not in fact found the target value even after left over equals to right, which paraphrased is, which means that we have searched every value in the array already using binary search, but we still haven't found target. That's why we will just return -1. So next we have greedy. So what is a greedy algorithm? A greedy algorithm is actually an algorithm that makes the locally optimal decision to attain the globally optimal decision. A key characteristic of greedy is that we will always make the best choice at that moment, and we will never revisit past decisions because we've already made the best decision at that point. So we will not want to revisit those decisions, since we already know that they are the best decisions we could have made at that point. Well, the time complexity of greedy algorithms, well, it depends on the question. For example, we have Dijkstra's which can run in O n log n time. But on the flip side, we also have traveling salesman, where the fastest known algorithm to solve the traveling salesman problem is actually O n squared times 2 to the power of n time complexity. And as Lucius said earlier, that is very, very bad. N squared is already a very bad time complexity, and multiplying it by 2 to the power of n just makes it even worse. We also have fractional knapsack, which runs in O n log n. All this really illustrates that the time complexity of greedy just depends on your question. For some questions, it might be n log n if you have to implement sorting of some kind, or it could just be a straightforward O n if you're not really sorting, you're just taking values as you go. So here is an example problem. This is NOI 2016 question 1. It's called lunchbox. I'll give you a bit of time to maybe search that in Codebreaker if you want to follow along with my explanation. Okay, so the abridged problem statement is we have n lunchboxes and m schools that request a certain number of lunchboxes. So we will let the number of lunchboxes a school requests be ki. What we have to do is maximize the number of schools that receive lunchboxes. So this is the example input. First of all, we have n, which in this case is 10, and 4, which in this case is m. Next, we will have ki, a list of ki, which is the number of lunchboxes each school is asking for. As you can see, this first school requests 3 lunchboxes, the second school requests 9 lunchboxes, and the third school requests 4 lunchboxes. And lastly, the fourth school requests 2 lunchboxes. The key observation we need to make here is that if we give lunchboxes to the schools that actually want less lunchboxes, we would have more lunchboxes actually to give to other schools. For example, if we have 2 schools that request 2 lunchboxes and 5 lunchboxes respectively, we would want to always select the school that only requests 2. Because if we select the school that only has 2, we have 8 lunchboxes left over. We can use these 8 lunchboxes to give to other schools, compared to 5. If we give that school 5 lunchboxes, we will only have 5 lunchboxes to give to other schools. This will allow us to give less lunchboxes to the other schools. So based on this observation, we would always want to pick the schools that require the least number of lunchboxes. So this is some example input. This is basically the input from earlier. We have 10 lunchboxes and these schools. Step 1, we have to sort them in increasing order. Next, we will give out to the schools with the smaller number of lunchboxes requested. So as you can see in this first one, 2 is the school that requires the least lunchboxes. So what we will do is give lunchboxes to this school and minus it from the available lunchboxes we have. Since we were able to give lunchboxes to this school, we will increase the number of schools we have fulfilled by 1. Next, we will move on to the second smallest, which in this case is 3. Again, we have enough lunchboxes to give to this school, as we have 8 lunchboxes available and this school requests only 3. So we will just fulfill this school's requirement and give them the lunchboxes and increase the number of schools fulfilled by 1, bringing our total to 2. And after that, we will go to the third smallest school. This school requests 4. Since we have 5 lunchboxes, and this school requires 4 lunchboxes, we can actually just give lunchboxes to this school. So we will give lunchboxes to this school and increase the number of schools fulfilled by 1. After that, we will go to the next item in the list. We will see that this school actually requires 9 lunchboxes, but we only have 1 available lunchbox left. Since we can only really give either 0 or all the lunchboxes that school requests us to give them, we cannot fulfill this school's requirement, and thus we just have to skip it. So this brings our final total up to 3. This is actually proven to be the most amount of schools that we can fulfill with the amount of lunchboxes we have. So what is the solution for this one? Firstly, we will import heap queue. This is actually kind of a priority queue module, but it is not the one we used in the data structures portion. It's actually quite similar though. And I'll explain it in terms of the priority queue syntax we learned earlier. So we will initialize n and m. We will map these inputs onto those two values. And we will have a C variable. This C variable actually stands for current, which stores the amount of schools we have fulfilled so far. Next, we will have a D array. This is basically going to be an empty list that we will turn into a priority queue using some of the heap queue functions. So first of all, we will take the this school and we will append it to our priority queue. Just ignore this and think of it as adding to the current priority queue. Next, while the means that while there are still schools that we can fulfill. So if D0 means that if the smallest element in the priority queue, just think of it as priority queue dot get. So if the smallest value in our priority queue is actually under equals to n being the amount of lunchboxes we have remaining, we can increment C by 1 and remove that amount of lunchboxes from the total amount of lunchboxes we have. If our current element is actually over n, or it's over the amount of lunchboxes we have currently, we just break the array. Since if we cannot fulfill the amount of lunchboxes for this school, we confirm cannot fulfill the request of all the other schools that are actually greater than this element. Finally, we will print the C value. So here are the pros and cons of greedy. One of the advantages of greedy is that it's actually quite simple and easy to understand. Next is quite efficient for certain problems, as you actually don't iterate over past decisions over and over again. This makes the time complexity largely quite fast. And this is basically what I just said. It's quite fast compared to brute force, because brute force iterates through every single possibility. But in that iterating over every single possibility, we might actually iterate repeatedly over certain decisions. And so impact the efficiency of our code. So the disadvantages of greedy. It doesn't always give the correct answer. A good example of this is basically every dynamic programming problem. With dynamic programming, you might first think of a greedy solution, but it's actually dynamic programming. And it's quite an abstract topic, so you might want to do some reading up on that one. So I'll explain another greedy question, which is actually not that easy to understand, but I feel it's good to explain to further your understanding of greedy. So the summarized question is, we have a class of n students. They each have 2 scores for both of their sciences, physics and biology. Physics is represented by AI, I being the number that the student has, or the index of the student, and BI, again, I representing the index of the student. Each score is a non-negative integer less than 10,000. We will need to select A students for the physics team and B students for the biology team to send for a competition, hence the name of the problem. So every student has to be in a team. That means we cannot just take the top few and then leave a few students out. Every student has to go for the competition. So we want to maximize the total score we can get. So what's the observation we need to make here? Let me illustrate with some of these sample input. So take this list of the physics and biology scores. Note that the amount of students that we need in the biology team is 1. The left row represents AI, or the physics scores of each student, and the right column represents BI, the biology student. So what would be the optimal decision to split the teams? So the optimal way is to have the best player go to biology and the other players in physics, obviously. But how do we tell whether a person would be better in biology than in physics? And in the previous question, it's quite obvious. This person got 100 in biology and only 8 in physics. So obviously we will want to push him to the biology team. But what if both of the scores are really, really high? Then how do you decide which one do we send for physics, which one would we send for biology? So the answer is actually to take the difference between the physics marks and the biology marks. But what do I mean by difference? Take the first player. The difference between his physics marks and his biology marks is 8 minus 100, which is physics minus biology. This shows that he has a difference between the marks of negative 92. What you will notice is that this difference actually represents the quote-unquote preference of a player for either subject. Since over here, the difference is negative, we can actually conclude that this student actually has a higher preference for biology than physics because the preference is negative. Another example is when the second player has 2 minus 1 equals 1 difference between their biology and physics scores. It shows that they actually prefer physics since the player had a positive difference score. It means that they actually scored higher in physics than biology. Thus, we should probably append that guy to the physics team. And circling back to our previous example, since the score is negative, it means that the player actually scored higher for biology than physics, since the difference between physics and biology is actually a negative number. As a result, we would want to append this student to the physics team. Biology team, since they scored higher in biology. So this is the sample solution. This is basically just the input. N, A, B, we will just put them in, N being the number of students we have, A being the number of people we want in the physics team, and B being the number of people we want in the biology team. Next, we will use A equals to a list. This will basically put all the elements in the line of input into this list. It's actually quite a convenient function. And personally, I learned this yesterday, and I found it quite useful. So first of all, we'll take our answer as the sum of A. But why? For this greedy to work, we would want to assume that every student takes physics. So why do we want to assume every player takes physics? It's because if we were trying to get the difference, we would want to let me rephrase that. Why would we want every player to take physics? It's so that we can find the players that have the lowest preference for physics and push them out of the physics team into the biology team. And this will let us keep the players with the highest physics score or the highest preference for physics in the physics team. I think the sample code later will actually illustrate this concept a lot better. So we'll loop through the lists and we'll get the difference between the biology and the physics grades. And next we will sort this. Now, what are we actually doing here? What we're doing is actually we're collating the difference between the physics and the biology grades and the physics grades and appending them to this B array. Next, we will sort the array. This and the reverse equals true means that it's sorted in ascending order. What this will actually do is sort the grades in terms of their preference. If the preference for the other subject is high, this will actually be at the top. And this kind of circles back to the answer equals sum A. So obviously we need B people in the biology team. Since we are assuming our sum or our total difference or total score is everyone's in physics, we want to push people to biology team. So what do? We iterate B times and we'll actually take the ith largest preference for the other subject. So what this basically did is it sorted B in terms of preference, and after that, we'll take the B largest preferences, people with the preference for the other subject. And why do we use answer plus equals BI? Since BI is our difference or our preference, this will actually add BI or the preference to the current answer. This will ensure that we get the highest total sum of scores for each team. Then after that, we print the answer. So how do you actually improve? What you should do is you should learn C++. First of all, it's quite a bit faster than Python. Secondly, you should watch some data structures and algorithms tutorials on YouTube. You can actually find quite a few of those just by searching them up. And a lot of them are actually quite useful. Secondly, you can learn more about computer science through the NUS C and C courses. They are pretty good, and it's even better if your school is actually paying for you to go to them. And you should join some Discord servers, such as the Codebreaker official Discord server. These are basically places for you to discuss or ask for help from people that are better at you than at programming so that you can improve. This is the link for the Discord server. And I think that wraps up my workshop today. The last few minutes until 6:05 is basically open questions. Feel free to send any questions you have in the Data Structures and Algorithms channel on Discord, and I will answer them right here. Okay, how do you know which library to use? Okay, this is more like, okay, so how do you know which library to use? Oh, okay. So to answer the goodness question, how do you really know which library to use? It's more like you look at the question and you observe that, oh, I can use a priority queue, or I can use a deck. And you're not really thinking in terms of libraries, you're thinking in terms of what data structures you need to use. If you know what data structures you need to use, then you can just simply import the library based on that. Oh yeah, and the video recording would be sent by the end of the day, yeah. Oh yeah, any more questions, feel free to ask. Was there any technical difficulties? What? Are you all at the how to improve slide right now? Wait, so you're at the correct slide right now. Yeah, for the coding thing, how do you know how to type? This one mostly just comes with practice. You practice more, you'll be able to more effectively know what you need to type in. Like how do you code the solution? Honestly, it just comes down to practice, practice, practice. Okay, please scan this feedback form right here to see, for us to know what to improve on next time. Yeah, I'll keep asking questions until 6 o'clock. And answering questions. Are there any other common / useful algorithms? Okay, to answer your question, yeah, there's a lot of algorithms available to you. Here we only really covered binary search and greedy, but there's actually a lot more, such as let me check my bank. We have actually the two pointers. We have dynamic programming and recursion, we just covered earlier. Then we also have some graph algorithms, which are quite fun. We have tree algorithms, which are quite advanced. There's pre-computation, which is kind of a technique. Data structures algorithms, and we have greedy. And there's also some classic techniques such as a sliding window, and etc. If you want us to cover those during June, just send it in the feedback form.